Hello everyone, thank you so much for watching my video today on two different tests for convergence. First is the comparison test for convergence, and the second is the alternating series test for convergence. Let's start with the direct comparison test. For the convergence test we've discussed so far, the terms of the series seem to be pretty simple, and the series must have a special look to it in order for the convergence test to be applied. Any slight deviation from that look or characteristic can make the convergence test non-applicable. A couple examples there. The first one is geometric, but this is not. This is a p-series, but this is not. All right? This is easily integrated, but this is not. So what are we going to do if it doesn't fall neatly into one of those packages? Our goal now becomes to investigate a way to compare a series with complicated terms to a simpler series with whose convergence or divergence is known. And here we have the direct comparison test. All right, so this only works if one series is always less than or equal to the other. If the larger series converges, the smaller series also converges. If the larger series diverges, then we can't say anything about the smaller series. If the smaller series diverges, then the larger series also diverges. If the smaller series converges, we can't say anything about the larger series. So let's look at a couple of using the direct comparison test. So here we have the first one, 1 over 2 plus 3 to the n. Okay, that does not look like any that we know perfectly, but we can compare it to this series here, which we can rewrite as which is just a geometric series. Okay, this is a geometric series that is convergent. Why? Because r is 1/3, which is less than 1. Therefore, it converges. Okay? This series would always be less than this series because our denominator is always going to be bigger than this denominator. So therefore, the actual term would be smaller. So since the bigger one we know converges, therefore the smaller one also must converge by the direct comparison test. Okay, so how we might say that? We might say, well, we know that 2 plus 3 to the n is always going to be greater than 3 to the n. Therefore, 1 over 2 plus 3 to the n is always less than or equal to 1 over 3 to the n. And therefore, since this series converges, this series would also converge. All right, next one here. Okay, we can compare this one to this series here. Looking at their denominators, let's try that again there. Looking at their denominators, 2 plus root n, 2 plus n. Pretty obvious that 2 plus root n is always going to be less than or equal to 2 plus n. Right? 2 plus n is going to be bigger. Okay? Unless n is 1, then it'll be equal to. Which means 1 over 2 plus root n would be less than or equal to 1 over 2 plus n. So this is the bigger series. Okay? So now let's take a look at this one here. It's pretty much the same thing as writing n equals 3 to infinity of 1 over n. These are the same series. It's different starting points, but they're the same series. Okay? This we recognize as a p-series. It's actually the harmonic series. And since n equals 1, or sorry, p equals 1, we would know that this one is divergent. It diverges. Okay? So since this one we know diverges, then we would say that, I put my sign backwards here. I just realized that right now. If the denominators are, if this denominator is bigger, then this would be smaller. So now let's go back here. Sorry about that. If this one diverges, and that's the smaller series, that means that the larger series must also diverge. Okay, so again, I screwed up my signs here. I apologize for that. We said this one was bigger than this one always, which is true. So therefore, the reciprocal of that would always be lower than the reciprocal of that, which means this series is less than this series. And since the smaller series diverges, the bigger series must also diverge. Remember that both parts of the direct comparison test require that 0 is less than a sub n is less than b sub n. So again, this is what we said before. If the larger series converges, the smaller one converges. If the smaller one diverges, the larger one diverges. If the larger one converges, if the larger one diverges, we don't know about the smaller one. If the smaller one converges, we don't know about the larger one. The next test is a limit comparison test. Often a series closely resembles a p-series or a geometric series, yet one cannot establish a term-by-term comparison necessary to apply the direct comparison test. If this happens, it may be possible to apply a second type of test called the limit comparison test. I suppose a sub n is greater than 0 and b sub n is greater than 0. And the limit as n approaches infinity of a sub n over b sub n equals L, where L is finite and positive. The two series, a sub n and b sub n, either both converge or both diverge. All right, so here's an example to use a limit comparison test. Show the following general harmonic series diverges. Okay, so if we don't know what this is here, what we can do is we can compare it to the series of just 1 over n, just a normal p-series. So what this is saying is if we did the limit as n approaches infinity of a sub n, which is 1 over a n plus b, over b sub n over 1 over n, which I'm going to simplify that here a little bit as well. It's going to be n over a sub n plus b. Okay. And then we recognize this is just a polynomial function of both 1 over 1, so it's going to be our limit's just our horizontal asymptote, which is going to be 1 over a, or we can use L'Hopital's rule to get 1 over a. And since 1 over a is finite and positive always, as long as a is greater than 0, which it says a is greater than 0 right there, then we would know that both these two would either converge or diverge. And since we knew that this one before, this one right here is divergent, we would know that the other one is also divergent. So we can say then, or therefore, both this series, which we knew from our earlier lessons, and therefore this one as well, are both the same, and they're both going to be divergent. Here's a couple helpful examples in choosing an appropriate p-series when using limit comparison tests. So I just got a couple examples for you there. You got something that looks like this. We want to use 1 over n squared, or change this to a cube or a fourth or a fifth, same thing here. Something looks like this, use n to the 1/2 in our denominator there. Get something like this, we can do n squared over n to the 5th, which is 1 over n cubed. Okay, and then going further than that, since here, this p-series, p is greater than 1, this one here, p is greater than 1, these both converge. Here, p is less than 1, it diverges. All right, let's do a couple of these here. Let's take a look how this will work. All right, so we're going to compare this one. I'll write that down. Compare with root n over n squared. So that's going to be n equals 1 to infinity of root n over n squared, or n to the 1/2 over n squared, or we can just write that as 1 over n to the 3/2, all right? So that's a p series where p is greater than 1, it's 3/2. So we know that one converges. All right, so let's see if we can get our limit to equal some finite positive number here. Okay, so limit as n approaches infinity of a sub n over b sub n, which I'm just going to flip and multiply. It's going to be limit as n approaches infinity of n squared over n squared plus 1. Again, you can think of that as a horizontal asymptote of 1 over 1, or use L'Hopital's rule. Either way, you're going to get 1 over 1, which is 1, which is positive and finite. Therefore, these two would do the same thing. And since the first one we already said converges, we could say this one also converges as well. All right, second one, we're going to compare this one to 2 to the n over n squared. Why n squared? Because n over n cubed, we can reduce to 1 over n squared. Okay, so this is going to be the series n equals 1 to infinity of 2 to the n over n squared. Okay, so first of all, that one, since we don't really know what that would be, we'd have to use the nth term test on that one, okay? And the nth term for that one would prove this to be divergent. Okay, so now let's see if our limit will produce a finite positive number. So we're going to go limit as n approaches infinity of n times 2 to the n, or 4n cubed plus 1 times n squared over 2 to the n. All right, so a couple of these things are going to cancel out on us here, as in these will cancel out, and then we're going to be left with n cubed or 4n cubed plus 1, which we can say is going to go to 1/4, which is positive and finite. So therefore, these two must do the same. And since the first one we already said would diverge, we didn't prove it because we did that in our last video, this one would also be divergent as well. All right, one more quick note on this. The polynomial test, this is not a test that will be covered on the BC test. However, it could be very insightful in determining the behavior of certain series. Basically, if we have a polynomial series, all right, so if the numerator is of degree j and the denominator is degree k, if j is less than k minus 1, this will converge. However, j is greater than or equal to k minus 1, this will diverge. Okay, and you can kind of think of that as the horizontal asymptote rules that we did back in pre-calculus, or maybe even algebra 2. What kind of a asymptote would it be? Would it be a horizontal asymptote? Would it be a slant asymptote? Would it have none of those asymptotes? That's kind of the same type of rule. Okay, the next test we're going to talk about today is the alternating series test. Up until now, most series we've dealt with have had positive terms. In this section and beyond, we'll study series that contain positive and negative terms. The simplest of these series is called an alternating series whose terms alternate signs. An alternating series is a series either the form, you can see the two forms there below, where a sub n is greater than 0 for all integers, n is greater than or equal to 1. Then we're going to multiply it by negative or positive, switching its sign each time. So, what is the alternating series test? The alternating series test says if we have an alternating series, they will converge if the following two conditions are met. The limit as n approaches infinity is 0, and a sub n plus 1 is either less than or equal to a sub n for all n. In other words, it's not increasing. Okay, it's either staying the same or decreasing. So we say that it is not increasing here. Okay, so let's take a look at a couple of these, determine the convergence or divergence of these. Okay, so first of all, we want to show that the limit as n approaches infinity of a sub n will be 0, which is pretty obvious. 1 over infinity would be 0. So the first part of our conditions is met. Well, first of all, we probably should say why we're going to use the alternating series test, because clearly this is alternating. Okay, so condition 1, we can put a 1 there if you want. Condition 1 is met. All right, condition 2 is we need to somehow show that this is not increasing. Okay, this one's pretty obvious to know. In this case, let's think of it this way: if n plus 1 would have to be bigger than n, right? That's pretty obvious here. If we're counting from 1 to infinity, n plus 1 would have to be bigger than n. So therefore, 1 over n plus 1 would be less than n, which means that this term would be less than this one always, which means the n plus 1 term is always less than n. So we just proved that a sub n plus 1 is always less than a sub n. So both of those conditions are met. Therefore, our original series is convergent. Second one here. All right, let's do limits as n approaches infinity of n over n plus 1. So we get infinity over infinity. If we use L'Hopital's, we get 1 over 1, which is 1, which is not 0. So therefore, since this is an alternating series and the first condition is not met, we don't even have to check the second series. We can already say this is divergent by the alternating series test. On the next slide, our last slide of the day here, just a couple different ways to show not increasing behavior. We can use the algebraic difference test to show that a sub n plus 1 minus a sub 1 is always negative, or 0. We can use the algebraic ratio test to show that a sub n plus 1 over a sub n is always less than or equal to 1. Or we can use the derivative of the related function f of x, for which a sub n equals f of n for all n, defined for x is greater than 0, and show that the derivative is always negative, or 0, which should show it's always decreasing. All right, so here's one last problem today. It's an alternating series, so we're going to use an alternating series test. Okay, so first let's prove the limit as n approaches infinity of 1 over 2n to the factorial, 2n factorial equals 0. Well, obviously, as n gets higher, our denominator is going to get bigger, so that's 0. Okay, so first criteria has been proven. Second criteria, we want to show that the terms are non-increasing, decreasing, or stagnant. Okay, so we're going to use one of these three up here. We're actually going to try to use the second one. Okay, so we're going to do 1 over 2 times n plus 1 factorial over 1 over 2n factorial. All right, if we flip multiply, we get 2n factorial over 2n plus 2 factorial. Okay, so we got to think about our factorial rules here. 2n factorial and then 2n plus 2 factorial. What is 2n plus 2 factorial? 2n plus 2 factorial will be equal to 2n plus 2 times 2n plus 1 times 2n times 2n minus 1 times ... 1. Right? What is 2n factorial? Well, 2n factorial is this. So really, if we had 2n factorial on the top, this would be up here, which means all that would cancel out. So I'm left with 1 over 2n plus 2 times 2n plus 1. which as long as n is positive increasing, which it is, this is always going to be less than 1. Oops, I put 0. I said 1 and wrote 0, but it's always going to be less than 1. Okay, because this is always going to be positive and bigger than 1. This will always be 1 over that would always be less than 1. Which means this is not increasing. So criteria 1 is met, criteria 2 is met. Therefore, this one also converges by the alternating series test. Okay, that's it for today. These two more tests that we learned today. I hope you enjoyed the video. We'll see you again soon.